Okay, it's about time to start. So first of all, welcome back. Tonight we finish up the unit on introduction to ordinary differential equations, and we start the last unit, which is on topics in ordinary differential equations. So what that means is we'll be starting with the handout, well, at least with the stuff that's covered in the handout on 210 variation of parameters. And then we'll be starting 3.1, which is eigenvalues, eigenvectors, and diagonalizing matrices. So I think what I will do for the most part is, let me switch cameras here. For the most part, I will I'll do examples rather than talk systematically through this. But there is some explanation here, and if you need or want some additional detail, this is a good place to go looking for it. In essence, tonight, we need to understand this formula and be able to use it. That's the where we're going with 210 on variation of parameters in the Brownian. So let me just try to give an overview here. Okay, 210 is actually on two topics. The first is the Brownian, and second is variation of parameters, which uses the Brownian, so we need to do that one first. There is a very helpful theorem in ordinary differential equations that says this: if you have a differential equation and compute its two of its solutions, second order equation, if you find two solutions, then you can tell whether you have those are linearly independent by computing the Brownian. Now, it turns out that the Brownian has application in both systems of linear equations and in higher order equations. So for us, the Brownian for second order equations is actually not all that helpful. But let me give an example here, and I can at least show you what the Brownian is, and hopefully convince you that this claims about it are true. So we're going to start with a differential equation, and I chose one that's simple enough that I can simply write down the answers. Cosine of 3x and y2 equals sine of 3x are two solutions. And probably you would all believe me if I say these are linearly independent. You can't take a constant times this one plus a constant times this one, add it up and set it equal to 0, and hope to solve that in any way other than setting the two constants equal to 0. So there is a way of telling with a quick calculation, though, whether two functions are linearly independent or not, two that are solutions to the same differential equation. You compute this determinant. First of all, the first row of the determinant is just the two functions, cosine 3x, sine 3x, and then for the second row, I put their derivative. So the derivative of cosine 3x is minus 3 sine of 3x. And the derivative of sine of 3x is 3 cosine of 3x. And for a 2 by 2, the determinant is straightforward. It's take the product down the main diagonal, 3 cosine squared 3x, minus the product down the opposite diagonal, And in that case, I'm going to have minus, but then there's a minus here. So those multiply together to give plus, and then sine squared of 3x. Now the claim is that if you're on any interval where these two functions are defined, and you're starting with an equation that has continuous coefficients, then this Vronsky is always zero or never zero on that interval. And the interval here might as well be the whole real line. These are both defined on the whole real line. All the coefficients are constant, so they're continuous on the whole real line. And sure enough, if you use a trig identity, sine squared theta plus cosine squared theta is equal to 1. So this thing is always equal to 3, and it makes no difference what x is. Now, this is the first property of the Vronsky is this. It's always going to be always zero or never zero on an interval where the coefficients are continuous and you're working with solutions to the same differential equation. Furthermore, if the Vronsky is not equal to 0, that means that the two functions are linearly independent. On the other hand, if the Vronsky is equal to 0, that means that they are linearly dependent. Now, with just two functions, of course, this is not always so terribly helpful. It's usually obvious whether two functions are linearly dependent or independent, but let me give you an example where it's at least slightly disguised. Let's take this one here. y1 equals sine x cosine x, product, and y2 is the sine of 2x. And it turns out they do solve the same differential equation, but I won't go into that detail right now. I want to focus on the Vronsky. So if I compute the Vronsky, start like this, and then we compute the derivative here. Well, derivative of sine is cosine, so it'd be cosine times cosine or cosine squared. And if I take the derivative on this one, I get minus sine, so it'd be cosine squared minus sine squared. And the derivative of sine of 2x is 2 cosine 2x. And if we compute the value of this determinant, let's see, we'd have this thing here, sine x cosine x times 2 times cosine 2x minus, oh, what a mess, sine x, sine of 2x rather, times cosine square x, and minus a minus would be plus sine of 2x sine square x. Now, this is supposed to be either identically 0 or never 0, but can we prove it? Well, let's see. I can if I give away the secret, but I'd like to avoid that. Let's do this. Right here, 2 sine x cosine x, that happens to be the same as sine of 2x. Okay, now I notice that I have a sine of 2x here, here, oh, and here, everywhere. Sine of 2x times the quantity cosine 2x minus cosine squared x plus sine squared x. But cosine square minus sine square, that happens to be cosine of 2x. Maybe I should put a note here, because cosine square x minus sine square x is cosine 2x. And so this thing is equal to 0. It's identically 0. By that I mean it's 0 all the time, not just for some special version of x. So that's the 0 function. So this is always equal to 0. That means that y1 and y2 are linearly dependent. Now, if you've only got two functions to work with and they're linearly independent, what that means that one of them is a constant multiple of the other. And if you know your trig identities, you've probably been sitting here suppressing a snicker, because I set this up so that they would be linearly independent. Let's leave this one as sine of cosine x. But this, sine of 2x, there is a trig identity that says that's 2 sine of x times cosine of x. And sure enough, y2 is just 2 times y1. So this was guaranteed to come out to 0. And I was trying to do it in some way so that I didn't use this identity here, but I think I did anyway. I used a couple of identities. Now, it would have been much, much easier to have just at the beginning say, oh, I recognize that there's an identity, and oh, this is twice that. That would have been much easier. I'm not saying that this is an efficient means of calculation, but what I am trying to do is say that the value of the Wronskian is maybe it wouldn't be obvious at the outset. And if you do the calculations, as long as you can evaluate all this stuff, you'll either get a 0 or you'll get something that's not ever 0. Now, you could stop right here. You could just pick a value for x, say 0, plug it in and see if you get 0 or not. Because the claim is that the Wronskian is either 0 for all x's in the interval, or it's 0 for no x's in the interval. So, and the interval in this case is the whole real line. Pick any differential equation for which second order linear ordinary differential equation for which sine of 2x is a solution. Well, that's not real hard. Y double prime plus, let's see, 4y equals 0. That would do it. If you take two derivatives on this, you'll get minus 4 sine of 2x, and minus 4 sine of 2x plus 4 sine of 2x is 0. So I got an equation easily. The coefficients are constant, so they're continuous on the whole real line, and therefore either this Wronskian is identically 0, it's 0 for every x on the whole real line, and indeed that was the case, or it's not 0 for any x on the whole real line. So what that would mean is you really wouldn't have to do this with the trig identities. You could pick an x, just anything convenient. How about x is 0 or x is pi over 2 or something like that? Plug it in here and you should either get a 0 or a non-zero number. Now, if I plugged in 0, for instance, this would 0 out, this would 0 out, this would 0 out, and I get 0. So, yep, sure enough, it's 0 everywhere. So that would be, you don't really have to do the trig identities in order to find this, just compute it at a point. It's 0 or it's not. Okay, and you could use a calculator. If it doesn't come out to something pretty close to 0, then you're probably safe. So these two are dependent because their Wronskian is 0. these two up here are independent, and their Brownian is never zero on the whole real line. And that's the point of the Brownian. Now, where the Brownian really is useful is what if you were solving a differential equation of, say, fifth order, and you got 5 of these functions now, and they're, they're relatively complicated. It might be really kind of hard to tell whether they are linearly independent or not. And what you would do in that case is you would write the 5 functions down, and then you'd take 4 derivatives to fill it out to get a square matrix, compute the determinant, and you're done. And you can do that with technology. You pick an x, and you evaluate all those functions. So now you just have a determinant of numbers, plug it in your calculator, boom, it's 0 or it isn't. So they're dependent or they're not. So that is the real value of Brownian. Now, the reason we care about the Brownian tonight is because it comes up in the formula for variation of parameters. So variation of parameters says this. And this turns out to be an incredibly powerful technique. It does, however, oftentimes generate a computational nightmare. So it's not the place you start usually. But here's what variation of parameters says. Suppose that we have some second order linear I have to write it and then I'll say it. Second order linear ordinary differential equation where all these coefficients, P, Q, and R, are continuous on some interval. So for instance, if they were constants, they would qualify, right? But notice, there's no assumption here that the right-hand side is 0. So we know in general that the solution for the system is going to look like YH, the solution to the homogeneous equation, plus YP, some particular solution. Now, we have some techniques for finding solutions to the homogeneous equation, but for a non-homogeneous equation, we don't have a lot at our disposal. What the tools for finding YP available to us so far are these. Number one, we do have this method of complex exponentials. That works only if the right-hand side is a single sine or cosine and the coefficients are constants. We have the method of undetermined coefficients. That works only if the right-hand side, it's a little bit more flexible. You could have sine and or cosine, sinh and or cosh, any polynomial, like x squared plus 3x minus 2, any exponential, or a product of an exponential with one of the things I said before. And in that case, once again, the assumption is you have continuous, and not continuous, constant coefficients. And now, what do you do if you don't fall into one of those categories? The third option is to use variation of parameters. And I think I kind of interrupted myself. I was telling you what variation of parameters says. It says if P, Q, and R are continuous, on an open interval, let's give it a name, I, then and if, I need a second assumption here, and if y1 and y2 solve the homogeneous equation, then a particular solution is given by yp equals minus y1 integral y2 r over w dx dt, whatever the independent variable is, plus y2 integral y1 r over w dx. So it's just a formula. And these are antiderivatives, indefinite integrals. So if you can solve the homogeneous equation, this says, then in principle, you can, no matter what the right-hand side here is, as long as everything is continuous, then you can write down a particular solution. And if you can get a particular solution and the homogeneous solution, then you can solve the equation. Now, in practice, this can be quite challenging. Oh, by the way, and I better write down in the formula here what we mean by W. It's y1, y2, y1 prime, y2 prime, take the determinant. So as long as we can find a y1 and a y2 that solve the homogeneous equation, and we can compute W, that's usually not a problem, and we can evaluate these antiderivatives, we're all set. Now, I should mention that there is a trick in case you cannot evaluate the antiderivatives. And there are antiderivatives that at least have no finite closed form. So for instance, this one here, e to the x squared dx, what's its antiderivative? Well, there isn't one that doesn't involve infinitely many terms. So what you could do though, is if you wanted to talk about this function as a function, is you could do something like this, usually change the letter in here. And let's say our interval that we're working on in this case was the interval we care about is 0 to infinity. That's our I. Well, then what we would do is we'd say, okay, the function is this, f of x is the definite integral from 0 to x of here to here. And then if you give a number for this, like 1.4, then you, on your numerical integrator, whether it's in your calculator or MATLAB or whatever you're using, you say, estimate the integral for me from 0 to 1.4 of e to the t squared dt. And that's very, very doable. So the fact that you can get this function in terms of antiderivatives, not all is lost, even if you cannot evaluate this. You could express the function in this kind of a way, and then if you needed its value at some number, then you'd get out the numerical integrator and it'll give it to you. So, and as long as this is a well-behaved function here, then you'll be fine. And on a short interval, this one is from 0 to 1.4. There's just no problem at all. You can estimate that very, very accurately. So what I want to do for the rest of this part of the lesson is to go through a few examples of this and just grind out yp, and well, actually we'll solve the whole equation. And there are multiple steps. One thing I want to mention to you, it's in the handout, but I should note right here is that the way this is set up, the leading coefficient must be 1. That's the standard form. The standard form is essential because that's what tells you what the standard form of R is. And R shows up here in the formula. So for instance, if you had Euler-Cauchy equation and you started with x squared out here, then the R that appears in that form wouldn't be the right R. Divide it through by x squared in order to get the right R. And I'll show you an example in just a moment so you'll see what I'm talking about. Okay, let's start with something relatively simple so we can at least see the technique. Y double prime plus 9y is equal to the secant of 3x. Okay, now, do I have continuous coefficients? Well, yes, they're constants. I have a continuous right-hand side. What's the interval? Whole real line would be, well, not quite. Secant, that has some vertical asymptote. So wherever the secant is defined on any one of those intervals would be fine. So for instance, this is 1 over the cosine of 3x. The cosine at 0 is 1. Just go a little bit on either side of 0 and you'd have a perfectly good interval. And we can write down two solutions in a pretty easily. You might just be able to look at this and say, oh, sine of 3x and cosine of 3x will do it for the homogeneous solution. So you want to solve this one first. But if that wasn't obvious, then what you do is say, oh, this is a constant coefficient, homogeneous, second order linear equation. We look at the characteristic equation. Be this, lambda square equals -9, so lambda is 0 plus or minus 3i. And we have a formula for the general solution of the homogeneous equation is this. It's this I think we called alpha plus or minus I omega in the formula. So e to the alpha t, a cosine omega t plus b sine omega t is the general solution. And the two solutions then would be the exponential times the cosine, exponential times the sine. In this case, though, the alpha is 0. So that's e to the 0t, that's just a 1. A cosine, now omega, in this case, is 3. So cosine of 3t plus b sine of 3t, that's our general solution. And you pick one of those to be y1, and you pick the other one to be y2. I'll do it this way, because if you put the cosine first, the Vronsky doesn't have a negative sign. But it's okay to do it the other way around. Okay, so let's compute W. We're going to need that. The formula is y1, y2. Take the derivatives of these, y1 prime, y2 prime, and compute the determinant. So y1 is, we might as well take y1, we can take any coefficient we want on that. So how about 1? Cosine of 3t, and y2, I'll take that to be 1 times the sine of 3t. Okay, so I've got cosine of 3t, sine of 3t. Then I take the derivative. The derivative of cosine is minus sine, minus 3 sine of 3t. Derivative of sine is cosine. That's 3 cosine of 3t. And then taking this product, I've got 3 cosine squared 3t. And minus a minus, that gives me a plus 3 sine squared 3t. Factoring off the 3. And I'm putting it in the order we're used to seeing it. Sine squared 3t plus cosine squared 3t. Well, sine squared theta plus cosine squared theta equals 1. So the Vronsky in this case is equal to 3. And now I'm ready to write down a particular solution, a solution that will satisfy this, namely, you plug the y that I'm yp in here, it'll generate secant 3x. Okay, this is what you do. The formula says it's minus y1 antiderivative y2r over w dx plus y2 antiderivative y1r over w dx. All right, y1. is cosine 3t minus cosine 3t integral y2, that's sine 3t, r, that's the right-hand side. And notice, this does have a leading coefficient of 1, so it's in the standard form. Secant of 3x over w dx. And I've got the first part written down, plus y2 sine of 3x integral y1 cosine of 3x. Oh, I'm switching between x's and t's here. I think they're all supposed to be x's. Secant, that's r, over w is 3. And I've not really got room for dx, but I'll scrimp something in there. Okay. This is not as awful as you might think. First of all, this 3 we just take to the outside. Now, secant of 3x is 1 over the cosine. So maybe I'm tempted to swoop through here and write down the answer, but that's not a good idea. If it's been some time since you've done this. So remember, I had a 3 here in the denominator, put it on the outside. All right, the derivative of cosine of 3x is almost the sine of 3x. We've got a constant to take care of. The derivative of cosine, first of all, is minus sine. So I'd like a minus here. So I'll put a minus here, and I'll cancel a minus there. And then I'd also like sine of 3x times 3 for the chain rule factor. So I should have maybe, let me turn that into a 3. Oh, and it's negative, right? So if that's u, then that part on the top is du. So this is the form du over u. Sine 3x, this one actually is pretty nice. Secant of 3x is 1 over cosine of 3x. So it's cosine 3x over cosine of 3x. That's just 1. And the only thing that's left is the 1/3. And then dx, or 1 dx if you like. Okay, now this has the form u under du. So that's log of u. Cosine 3x over 3 log absolute cosine 3x. That's this one. And this one is nice. Antiderivative of 1 is x. So it's x sine of 3x, and you might as well say x over 3, right? So there's our yp. And the general solution, I'm going to have to cheat a little bit with notation because it won't all fit. Y is equal to YH, so that's C1Y1 plus C2Y2, and then plus this stuff here, and I'll say plus YP, because I've just got YP on the previous line. So it's kind of a big formula, but you do it, you compute it, all this stuff in a systematic way, and it just uses things we've seen before from ODEs and some stuff from calculus. So that is the general solution to this ordinary differential equation. Any question about that? Okay, let me push through to another one, and I think sometimes just more examples are more helpful than long discussions. And this time I will try to say less and just do the calculation. And I think that's supposed to come out okay. Now, most of us would look at something like this and think, I don't think I can guess the answer, right? This is fairly challenging, but we have a method now. So our method is this: let's find two linearly independent solutions to the homogeneous equation. So a lot of times we just say, find the homogeneous solution. Well, you start with a characteristic equation, lambda squared minus 4 lambda plus 5 equals 0. Huh. That's not real nice. Lambda equals negative b, it's 4, plus or minus the square root of b squared, 16 minus 4 times a times c, 5 over 2a. And it looks bad, but it's not too bad. Let's see, 16 minus 20 minus 4, so that's 4 plus or minus 2i all over 2. And so lambda 1 and 2 are 2 plus or minus I. Now we have a formula for what you do with a complex conjugate pair for roots of the characteristic equation. And the answer is y equals e to the alpha x a cosine omega x. That's just 1 times I. So y1 is e to the 2x cosine x, and y2 is e to the 2x sine x. W. Well, e to the 2x cosine x, e to the 2x sine x. And now we're going to take derivatives. All right, derivative of e to the 2x is 2 e to the 2x times cosine. And then when I take the derivative on cosine, I get minus sine, so that's minus e to the 2x sine of x. And the second one, very similar, 2e to the 2x sine x. Taking the derivative on the sine, I get a plus cosine. So e to the 2x cosine of x. And that's a determinant. Okay, notice every single thing has got a factor of e to the 2x. And when you take the product down this diagonal or that one, you get a pair of those. So e to the 4x multiplies every single term. We could just peel that off and check and see what we've got. Okay, we will have 2 sine x cosine x, which sounds familiar. And this times this, cosine square x. Subtracting what you get down the other diagonal, let's see, we'll have 2 sine x cosine x, but we're subtracting. Well, that's convenient. Those things are going to drop out. And then we have minus a minus, so plus sine square x. All right, 2 sine x cosine x, that is, there is a trig identity, that's sine of 2x, but it doesn't matter because I got a positive 1 and a negative 1, so those add out. And then here, once again, sine squared x plus cosine squared x, that's 1. So the Vronsky in this case is e to the 4x. All right, we're ready for the killer formula. Yp equals minus y1. By the way, I am modeling this behavior because I'm encouraging you to do it. When it comes to the exam, you don't want to be stopping and very nervously trying desperately to remember this formula, right? You want it to be there. And if you get in the habit of writing it down every time you solve one of these problems, you'll just accidentally memorize it. So I encourage you to get in the habit. So it's minus y1 times the integral y2r over w dx plus y2 y1r over w dx. We did indeed start with the standard form. The leading coefficient is 1. So this monstrosity on the right here, e to the 2x cosecant of x, is r. Okay, so minus y1. Well, y1 was what? E to the 2x cosine of x. Antiderivative of y2, e to the 2x sine of x, over w. W is e to the 4x, I think, wasn't it? Can't see it. Here it is. E to the 4x. And r is e to the 2x over sine x. Let's write it that way. Cosecant is 1 over the sine dx. Now, the intermediate steps were kind of impressive, but this is really convenient. Sine x over sine x, that's 1. E to the 2x times e to the 2x divided by e to the 4x, that's 1. This integrand is just 1 here. So that's looking good. So minus y1, I lost my minus sign. Plus y2, e to the 2x sine of x times the antiderivative of y1, which is e to the 2x cosine x, times r, e to the 2x over sine x, divided by w, which is e to the 4x. So all the scariness goes away here. This simplifies to 1. Antiderivative 1 is x. So I've got minus x e to the minus 2x cosine of x. This one, on the other hand, takes some work, but hopefully not too bad. This is convenient. E to the 4x divided by e to the 4x is 0. And then we've got sine on the bottom and cosine on top. Well, the derivative of sine is cosine. So this is a logarithmic form. Natural log, absolute value, sine of x. So as horrible as it looked along the way, it did turn out to be something fairly nice. And then the general solution to the homogeneous equation is, I think there's just room to do it here if I'm careful. C1 times y1, which is e to the 2x cosine x, plus C2 times y2, e to the 2x sine x, plus yp, which is this thing right here, and already made a mistake, should be a minus, not a plus, minus x, e to the minus 2x, cosine 2x plus e to the 2x sine x log absolute sine x. And once you do a few of these and you see the complexity of the things that pop out, you begin to appreciate the power of this formula. You know, how would you ever guess that? I don't know. You need a method, and this is one.
Does it ever happen that the W is 0?
If the W is 0, it means that your y1 and y2 are not linearly independent. And that means you didn't have a basis for the solution space of the homogeneous equation, and therefore this formula doesn't apply.
Okay.
Now, if it does happen, not all is lost, because that would tip you off right away. Oh, I need another linearly independent solution for my homogeneous equation. And so if you got a 0, the truth is it's probably a mistake. And then that would just clue you in to go back and see what went wrong.
Where'd you get the negative on the exponent in the YP there?
I think that just popped in sort of gratuitously, and now it's going to disappear in the same way. But this minus is intentional here.
Yeah.
I like stable solutions. These ones with positive exponents, I mean, those are going to blow up over time. So it's my personal prejudice coming out in that. You look like you're pondering. Sam, any questions? Any follow up here? Or? Just a lot. Huh? Yeah, it is.
I have another question. Why would we choose to use this one instead of one of the other two methods? Other than this case where there's more than one function on the right.
Yeah, to rephrase the question, why would you ever do this if you could avoid it? And the answer is you would not. If you can think of a way of avoiding this method, do so. Because clearly, remember when I introduced it, I said it oftentimes generates a computational nightmare. And you know, you're having at least bad dreams here. They might not be nightmares, but they're getting there. I was commenting before class that I was trying to find examples that were non-trivial. But you know, I don't want them just all the integrals to be of 1 dx or something like that. But on the other hand, they should be doable. And it's not easy. If you just sort of pick one at random, you probably generate an antiderivative you don't know how to evaluate. Now, that's not a total loss, as I pointed out earlier. At least you can do something with it numerically. But, and in a lot of engineering situations, that's good enough. But surely, if complex exponentials or undetermined coefficients or taking a wild guess and checking will work, you should do that.
So what's the case in which we have to use this one?
This one right here is a case. Now, I do have constant coefficients, but I don't generally have a way of dealing with a cosecant here.
Oh, okay.
Sine and or cosine times an exponential, yes, is okay. But cosecant, generally not. Now, does that mean you couldn't possibly guess the solution? And keep in mind, we know what the solution looks like. It's here. Well, some people are really clever, and some people are really lucky. So maybe you could. But for me personally, I think it would be quite difficult for me to guess that. Okay, let me show you one now. I really need to show you another sort of problem, because this comes up in the homework, if nowhere else. And if I don't alert you to it, I said something in general earlier, but general comments usually are not that helpful. This one has a trap waiting for you to fall into it. And I'm carefully copying from my notes here because with these problems, there's some things like constant coefficient, homogeneous, second order linear equations. You just sort of spray some coefficients in there and you're going to be able to solve the problem. It might be you might get 6-digit denominators in your fractions or something, but other than that, you can do it. These, they're very finicky. You just change a little bit and boom, it gets awful. But I think I copied it correctly. And now I want to solve this equation. Now, the first thing I need to do is solve the homogeneous equation. And for the homogeneous equation, this is a Cauchy-Euler equation. And we know that you compute the auxiliary quadratic, m squared plus, then it's this coefficient here, -4 minus 1, m plus 6 equals 0. Or if you did it the way I was doing it in class, you go m minus 1 minus 4m plus 6. These are equivalent. And if you do one step of simplification, m squared minus 5m plus 6, you get this. So either way you like to do it, doesn't matter. Okay, now m squared minus 5m plus 6 equals 0. That does factor. M minus 2, m minus 3. So far, so good. So m equals 2 and 3. And that means y1 equals, say, x squared, and y2 equals x cubed. These are two solutions to the homogeneous equation. And honestly, after some of the stuff we've looked at already tonight, just plain old powers of x, oh, thank goodness, what a relief. And now we're going to compute the Vronsky. So I've got x squared, x cubed, 2x, 3x squared. And down this diagonal, I get 3x to the 4th. Subtract this product, 2x to the 4th equals 1x to the 4th. That's a pretty nice Vronsky. So looking good. Now, at this point, yp equals minus y1 times y2r over w dx plus y2 integral of y1r over w dx. And the very next step you make is likely to be an error. And here is why. Notice the leading coefficient on our ODE is not a 1, it's x squared. So in order to apply the formula, in order to apply this formula here from variation of parameters, your r has to be the one that comes from having a 1 for a leading coefficient. So now this is no problem as long as you notice. All you have to do is divide through by x squared. So you have y double prime minus 4 over x y prime plus 6 over x squared y equals 7x squared sine x. So the only catch is when you go to fill in the blank here for r, you want to use 7x squared sine x, not 7x to the 4th sine x. So why? Because you got to divide out that leading coefficient of x squared. All right, so we're ready now, and we hope that this comes out okay. Minus y1 minus x squared integral y2 is x cubed. R, we now are clued in, it's 7x squared sine of x over w. W is x to the fourth. Oh, my word. Dx plus y2. Y2 is x cubed. Integral y1 x squared r 7x squared over sine of x, a times sine of x, over w, which is x to the fourth, dx. And it probably won't win any awards for popularity, but it could be a lot worse. Okay, I've got 7x to the fifth up on the top here, and I've got x to the fourth on the bottom. I'll put the 7 on the outside, and I've got an x left over here, x sine x, for my antiderivative. That requires parts, but you know, at least it's doable. Here I've got x to the fourth over x to the fourth, so those just cancel out. The 7 can come to the outside, and I have integral of sine of x dx. That's easy. Okay, parts formula. I don't really have a good place to write here, so I'm going to write it on the side here. If you've not used it for a while, integral of u dv is equal to uv minus integral v du. That's the formula. So we need to pick one of these things to be u, which in this case probably should be the x, and dv is sine of x dx. Okay, so I've got minus 7x squared times some stuff. uv. Well, what has derivative? Sine of x? Negative cosine does. So minus x cosine x minus, this is the minus from the formula, v, that is minus cosine of x, and then du is just dx. Oh, that's good. We can do that one. Plus 7x cubed, and then let's see, the derivative of cosine is minus sine, so this actually needs to be a negative cosine of x. We're almost there. Minus 7x squared times, let's see, derivative sine is cosine, so this is sine of x from this antiderivative minus x cosine of x minus 7x cubed cosine of x, and that is minus 7x squared sine x plus 7x to the fourth, or rather third, 7x to the third cosine of x minus 7x cubed. Oh, look at that. Cosine of x, those two last terms add out. Minus 7x squared sine of x. And this one is simple enough. You know, you might, by guessing and checking, you might, especially if you have like a calculator that does derivatives, you might guess it. I see a couple of people looking closely at that. Is there a bug or just looking? I consider all of these tentative until they've been checked. And by this point in the course, you know why, right? So easy, drop a minus sign. A 2 turns into an n or some such thing. Minus signs appear in exponents. Why? Because we're humans, not computers. And then, of course, the general solution would be c1x squared plus c2x cubed plus this. Oh. Okay, that is variation of parameters. And what it comes down to is a formula and enough practice to be able to use it efficiently. The other catch, of course, is you can get into some heavy weather on the antiderivatives. So going back and reminding yourself of some antiderivative formulas from Calc 2 is probably not a bad idea, especially if you haven't been using them for a while. If you're fortunate enough to have come right out of a class where you're using that stuff, then you're good to go. But I can say anything really good for me about the first 5 years of teaching is I finally got to where I remembered all the stuff from Calc 2. I didn't have to look it up all the time. Maybe I shouldn't say all of the stuff, I probably forgot some. I need to do integration by parts. I don't anymore have to look up the formula. It was not always the case. Okay, that is variation of parameters in the Brownian. And now you know when I flipped over here and I said, well, Brownian is there. And the key formula is here. And if you can do that, you're in pretty good shape. And of course, you practice. And there are some problems to work out. All of them, in this case, I borrowed from my good friend Kreitzig. And the reason I did it primarily is because then I can take his solutions and I don't have to work them 6 times to make sure that I got them right. And then you have something to look at, you know, when you do some long calculation like this, it's kind of satisfying to look at the answer list and say, oh, yeah, that's equivalent. Okay, well, that was topic 1. And congratulations, you have endured the first 2/3 of the course. The remainder is on topics in differential equations. And the first one is essentially how to solve systems of linear equations. Now, as usual, we're short on time, so I will give you the Cliff Notes version of how to solve at least homogeneous systems of linear equations. So I am thinking of a system, maybe I should just look through my notes here and pick one that actually appears. So I'm thinking of a system of linear equations like this. Y1 prime equals 4y1 minus 2y2. Y2 prime equals minus 2y1 plus 4y2. Now, a a reasonable person might ask the question, why would we ever want to study something like that anyway? After all, mathematicians just make this stuff up so that they can publish papers and get tenure and then promotion. And the answer in some cases is yes, they do. But in this case, it was invented because it's useful. And in the notes, I talked through some example. For instance, suppose we had mixing problems before where I had some salt in a tank of water, and you have some solution running out, and you have some either pure water or some known concentration pumping in, and you can use a linear differential equation to model the concentration of salt in the tank, or the amount of salt in the tank. Well, what if you had this sort of a situation now? You have two tanks. So two tanks are sitting here. And the mixing works like this. You've got a flow coming over here, and you got a flow coming over there. And then you might also have like an input or an output on either one of those. So you'd have amount of salt in this tank might be Y1, the amount of salt in this tank might be Y2, and this would be the kind of system that you would set up. This is homogeneous, so I don't have anything either net going in or going out. But, you know, suppose this one was dramatically more concentrated than that one. Then it would be nice to be able to set up equations that would tell you, now you know what's going to happen. In the end, you're going to get the average concentration, right? But it would be nice, especially if these have dramatically different volumes, to have a system of equations and then a solution that tells me, oh, at time t, I expect the concentration in tank 1 to be this and in tank 2 to be that. So this would do it. Another case would be, we talked about a mass spring system for second order linear equations. Well, what if you had a mass and then you had another spring and then you had another mass? Well, now you can imagine that these things can vibrate in very complicated ways. One mass can go up while the other one's going down because you're just getting some pretty wonky stretching in the springs. And this would be modeled with a system of equations. So, so there's good reason to care about systems of equations, and we're doing them because they're applicable in the sciences and engineering, and presumably that's why you're here. Or another possibility is you heard how fascinating my course in this topic was, so you came from afar to see if it's really true, and behold, it was, right? No one's raising their hand saying, yes, that was me. Okay, well, I'll go on hoping for that day. Okay, now, this can be written in matrix form, just like you could any other equation. So I could say this is the vector with y1 prime and y2. These are functions now, of course, probably of time. And this would be a matrix 4, -2, -2, 4. And then you have y1 and y2. And if you write with at least one common notation, you'd say this is the vector y, and we're taking its derivative. So vector y prime equals a matrix coefficient times the vector function y. And if you wanted to write your independent variable in there, you could. The bars really mean something here now. They mean we're looking at vectors and matrices. And I've kind of obliterated my prime mark there. Made it part of a parenthesis. By the way, another common notation is the dot notation for time derivative. So you will see that in science and engineering. That means the derivative with respect to time usually. So we'll stick with the prime because it's familiar. But if you come across the dot, don't be puzzled too long, just means derivative. Okay, now how would you go about solving one of these things? Well, if you remember, this kind of sort of looks like this situation, y prime equals 3y. Let's just not vectors now, just simple functions like in Calc 1 and Calc 2. The solution to this would be y equals e to, well, some constant, c e to the 3t. When you take the derivative, you do in fact get a chain rule factor of 3 popping out here. So it wouldn't be unreasonable to guess that y has this kind of an appearance. It would be some vector, let's say v, times e to the lambda t for some eigenvalue, just like we had for second order differential equations. You might see something like that. Now we have no guarantee about this, but we're just saying, you know, if it followed by analogy what we have here, then you might see something like this. And by the way, when this is the common notation for systems of differential equations, but this means scalar multiplication. This is a scalar here. This is a vector function. No, this is just a vector, a fixed vector. So if you see something like this, 3 to e to the 2t, it means 3 e to the 2t and 2 e to the 2t. It's just writing the scalars on the right side of the vector instead of the left. Okay, so a good guess would be that you might be able to find solutions of this form, and it turns out you can. We are going to be defining in just a moment what we call a eigenvalue and an eigenvector. And they come in pairs. So you have a number, a scalar, usually called something like lambda 1, lambda 2, something like that, and you have a vector that goes with it. And for a 2 by 2 matrix, the best you could hope for would be two of these pairs. And it turns out that in a case like this one, if you can find a pair of vectors and eigenvalues, then the solution would be this. And I'm not trying to justify it right now, I'm just reporting. It's C1, V1, e to the lambda 1t plus C2, V2, e to the lambda 2t. So if you can find these vectors and values, scalars, the eigenvalue and eigenvector pairs, at least enough of them, then you can write down the general solution to this system of equations directly. So that is the motivation for what we are about to do. Now, there are two ways of looking at this. Let me give you another perspective on this. This perspective is, I hope it sort of kind of looks like what we get with scalars. And then I say, poof, there it is. Proof, none, whatever. I just put it on the paper here and hope you believe me. But you can look it up, it really is true. Another thing would be to look at a special case. What if you had a special case like this? 3, 0, 0, 2 is my matrix. Y1, Y2. And here, I want Y1 prime, Y2 prime. For some reason, mathematicians don't use this language, but engineers do, and I think it's actually helpful. They say this is a decoupled system. In other words, what Y2 does has no influence on Y1 and vice versa. So it would not model something like two masses connected by a spring. Those masses are influencing each other. If you wrote this out, this top line would say 3y1, and the bottom line would say 2y2. And so it's just a pair of independent equations. Y1 prime is 3y1, and y2 prime is 2y2. And you can actually solve those. Y1 equals e to the 3t, and any constant multiple of it. And y2 is e to the 2t, and any kind of constant multiple of that. So if I took the derivative of this, I would indeed, y2 prime would indeed be 2 times y2. And y1 prime is in fact 3y1. So this actually fits that pattern. YH is equal to a certain vector, in this case, this one, C1 e to the 3t plus C2 times a certain vector, the eigenvector in this case would be that one, times e to the 2t. So in this special case, what I claimed here actually works. And in fact, it always works as long as you can find the eigenvalues and eigenvectors. Okay, so apparently eigenvalues and eigenvectors are a thing. People look for them. And you are among those people as of tonight. So what do we mean by these things, and how do you find them? All right, an eigenvalue lambda and its eigenvector v, they come from a matrix, okay? From the matrix A means, if we have them, it means this. If you take the matrix A, left multiply the vector v, you get a scalar times v. And in some cases, these are incredibly easy to pick out. And in some cases, they are, well, they don't even exist. But I was just making one up. Oh, I put it on the back side here. Let me refer to that. 0302. No, 3002. That's what I had. And you'll notice that one of the vectors I had in my solution was this one. And notice that if you multiply this, you get 30. And that is 3 times the vector I started with. So this eigenvalue for this matrix, this eigenvalue is 3, and the eigenvector is 1, 0, or any constant multiple of it would work, except of course 0. And there's another eigenvalue, an eigenvector pair. That's the one you get by picking off the second column. 0, 1. That does give you 2 times 0, 1. So the eigenvalue equals 2, and the eigenvector is 0, 1. Now, normally they're not this easy. So how do you find these things if they aren't just sort of looking at you when you take a look at the matrix? Well, let's write down this equation. what we're saying, in order to have an eigenvalue, eigenvector pair, is that AV equals lambda V. Now, you could write it this way. AV minus lambda V is the zero vector. But this isn't so helpful because this one has a scalar and a vector. This one has a matrix and a vector. So you can't even factor the V off because that would leave you with A minus lambda, which makes no sense. A matrix minus a scalar, you know, they don't match. But you can fix this problem by inserting the identity matrix. And now you can factor the V off to the right. A minus lambda I times V equals 0. All right, now, let me be more precise about what we're really looking for. If I come up with any square matrix, whatever, and any lambda, whatever, I am certain that every single one of you in this room could give me a solution to this equation. Because sooner or later, someone is going to say, I could use the zero vector, right? And so no matter what I write, you'd say, I solved it, professor, I got it. Give me my A and I'll be on my way, right? Well, and of course you'd be right, you would have solved it. So in order to block that easy passage, what we say is we don't want V to be the zero vector. And in other words, we know that solution is there. We're interested in are there any non-trivial solutions to this? Now, if there are, that means we have, this is a matrix then, right? And it's kind of a messy thing we've got written down here, but it's just a matrix. A matrix times V is equal to zero vector. That means that this V is in the null space of the matrix on the left. And we know that this matrix is going to have, the null space is a vector space. It's going to have a basis, and we'll be able to specify as many linearly independent options here as the dimension of the null space of this matrix. Now, some matrices do not have anything but zero in their null space. Think about the identity matrix, for instance. It doesn't zero out anything except the thing that starts with zero, the zero vector. So the only time that you can't get a non-trivial solution unless this thing here is singular. It has a non-trivial null space, in other words. So we want a non-zero solution, which implies A minus lambda I is singular. It isn't invertible, which would be equivalent to saying this: the determinant of A minus lambda I is equal to 0. And all solutions to this, all lambdas that make this true, will be the list of eigenvalues. And then once I have an eigenvalue, I find a non-trivial vector, or as many as I can, in the null space, and there's a vector that goes with it. Okay, so at this point, I think I've said enough in general. It would be probably helpful to actually pick a couple of matrices, find the eigenvalues, find the eigenvectors that go with it, and then show you some interesting feature of it. Okay, so I'm going to start with a matrix 4, -2, -2, 4. And you could think of this as essentially specifying a a differential equation, y prime equals ay, right? So you could think, I'd like to be able to solve this, or you could think, I would like to be able to find eigenvalues and eigenvectors to this. They're very closely connected questions. So what we would say is, what we would like is the determinant of a minus lambda I. Now, in this case, you know, we've got something concrete here. Here's what A is. Minus lambda I, well, I, the identity matrix, just says one's down the diagonal and zeros elsewhere. And if I multiply it by lambda, I have lambdas down the diagonal. So I want the determinant of that thing. And that is the determinant of this matrix right here, 4 minus lambda, negative 2, minus 2, 4 minus lambda. Okay, and since it's a 2 by 2, the determinant isn't too hard to get. It's 4 minus lambda squared, or you could say lambda minus 4 squared, wouldn't matter. And this times this, plus 4. Wrong, minus 4. And what we're doing is setting this equal to 0 because we want a non-trivial solution to y prime equals ay. We know that 0 will work in there. Okay, so, well, when you square that out, you get lambda squared minus 8 lambda plus 16 minus 4 equals 0. So that's lambda squared minus 8 lambda plus 12. And let me see, will that factor 6 and 2 will do. Lambda minus 6, lambda minus 2 equals 0. So I do know what values will work in this equation, determinant a minus lambda I equals 0. 6 and 2. Those are the eigenvalues. Of the matrix 4 minus 2 minus 2, 4. Okay, let's figure out the eigenvectors that go with it. Eigenvectors, well, I'm looking at this matrix here. 4, I'm leaving a little bit of space because I need to subtract constants down the diagonal. Okay, so I'll start with this matrix here, and let's start with 6. So I'll just label this lambda equals 6. I'm computing for that one. You subtract 6 down the diagonal, and you would like to find a vector x1, x2 here that generates the 0 vector. You're looking for a non-trivial vector in its null space. So let's see. To simplify this, 4 minus 6 is negative 2, negative 2, negative 2. 4 minus 6 is negative 2. Oh my goodness. Well, how about 1 minus 1? These columns are the same. So if I take 1 times the first column minus 1 times the second column, I will in fact get 0. By the way, for small matrices, this is usually how I get the eigenvectors. For 2 by 2s especially, I write this down and I guess and check. And it works pretty well with a 2 by 2. So this is an eigenvector. Now somebody could say, oh, no, I think minus 3, 3 is better. Well, okay, it's fine. What you're doing is taking mine and multiplying it by negative 3, right? So as long as you don't multiply by 0, you will have a valid eigenvector. So minus lambda equals 6, and let's call it v equals 1 minus 1 is an eigenvalue eigenvector pair. How about lambda equals what's the other one? 2. Well, you start with your matrix, 4 minus 2, 2 minus 4, and I subtract 2 down the diagonal. So 4 minus 2 is 2. And 4 minus 2 is still 2. I want to multiply by a vector, a non-trivial vector, to get the 0 vector. Well, it looks like these two columns are negatives of each other, right? So apparently 1, 1 would work. Okay, so y prime equals ay. That differential equation, here's the solution. Y, now this is considered a homogeneous equation because it's y prime minus ay equals 0. And I should be putting bars on this. It's a homogeneous equation, so there's no yp to worry about. And the general solution is C1 times V1, 1 minus 1, e to the lambda 1, t, plus C2, V2, times e to the lambda 2, t. Or to write out the solution without vectors, we're saying this. If you take C1 e to the 6t plus C2 e to the 2t for your first function and minus C1 e to the 6t plus C2 e to the 2t for your second function, it will solve the original system of equations, which we wrote in vector form way back here. But that would be y1 prime equals 4y1 minus 2y2, etc. Okay, so if you can find the eigenvalue and an eigenvector that goes with it, and you've got enough of them, in this case 2, then you can write down the general solution to this differential equation, which is why we're doing this. Now, I'm doing all this without much motivation because the last time around I did this, I developed the theory first because I'm a big picture person and I like to know why. I don't really like it when someone just hands me a formula and says, here, do this. And I say, why? And they say, don't argue with me, just do it. It works. Well, you know, I feel the need to find out why it works. And the problem was that in the explanation for why it works, there's sort of a long circuitous thing you can do that says, in essence, look, it works. So then I found that when it got to the exam, I had a number of students who were still doing the long circuitous thing that shows that it works, rather than just, you know, coming up with the eigenvalue, eigenvector pairs and writing down a solution, which is what I wanted them to do. So I'm showing you the short way of solving a system of equations like this first, because I want to get this in your head first. And then if you miss something later, you can at least solve the equation. Okay. Now, it turns out that that there is another property that comes from these two vectors, which is really quite remarkable. So what we have is for lambda equals 6, we have this vector, 1 minus 1. And for lambda equals, what was it? 2? Yeah, lambda equals 2. I've got 1, 1. This matrix that we get by just sort of pasting these two columns together, 1 minus 1, 1, 1, is interesting in its own right. If you, now, we have one other matrix running around in this problem, and that is the original matrix that we found the eigenvalues and eigenvectors for, 4 minus 2 minus 2, 4. And unfortunately, I forgot my calculator tonight. But if you will, let's give this a name. Oh, sure. This looks like a well-loved calculator.
I bought it from some kid for $40.
Oh, really? Okay. Well, that's a good price. All right, so let's go to matrix. I am going to put in A, the thing that I called A here. So that's a 2 by 2. 4 minus 2 minus 2, 4. And that one's in. And for B, let's put in this matrix. Let's see, whoops, 2 by 2. 1, 1, minus 1, 1. Okay, so I should have my A and B in here. I should probably check because it's easy to. What's with the double? Mine doesn't put these extra pieces in here.
I have no idea.
Me neither. Okay, which isn't really reassuring. Okay, I'm going to go back to the matrix menu here, and I'm looking for inverse, wherever that is. Oh, come on. Oh,
Isn't it just the matrix button?
yes, it's not. It's not in here. I swear, every 10 days I don't do matrices with a calculator. I forget how they work. B inverse A, I think this is what I want. If not, it's the other way around. B, aha. If you start with this matrix, which is the matrix of eigenvectors, compute the inverse, multiply it by A, multiply it by this P matrix again, you get a matrix that has the eigenvalues down the diagonal. In this case, 6 and 2. And the order of the eigenvalues is the same as corresponds to the order of the eigenvectors. This vector goes with lambda equals 6. I put that first, so it appears first on the diagonal. I put the vector for lambda equals 2 second, and so that appears second down the diagonal. Okay, so this is called diagonalizing a matrix. So how do you diagonalize a matrix? The answer is this. You first of all find each of its eigenvalues. You find as many linearly independent eigenvectors as you can for each of those values. If the total number of linearly independent eigenvectors adds up to the dimension of the square matrix, this only works for a square matrix. In this case, it's a 2 by 2, and we got 2 of those guys. Then you create your P matrix like this, and P inverse AP is guaranteed to be the diagonal matrix D that has the eigen values down the diagonal. Now this is pretty handy because if you think about it, when I was describing differential equations right at the beginning, I gave an example like this that perhaps seemed a little bit trivial. Well, what if we just had a diagonal matrix and we were trying to solve the differential equation like so? Then I said it turns out that the first one would be would be 0, 1, 0. Here we go. 1, 0, e to the 6t, and y2, you get 0, 1, e to the 2t. And that e to the 6t and e to the 2t are the functions that pop out of this. They're also the one that pop out of this. But notice, if we had diagonalized this first, we could have predicted that, right? So it turns out that diagonalizing matrices is very closely connected with solving systems of linear equations. And how all that connection goes is something that we'll describe in more detail in later lessons. But for now, take it, these are the take-home points. Number one, if you can find the eigenvalues and eigenvectors, you can immediately write down solutions to the system, the homogeneous system of equations, as we did here. So I found eigenvectors, I found eigenvalues that go with it, and that allows me to write down the solution. If you get as many of those as the dimension of the matrix, then in fact it's the general solution. You found them all. Number two is, if I can do that and I have enough of these eigenvectors to make a square matrix out of by stacking them up thusly, call that matrix P, then P inverse AP is guaranteed to be a diagonal matrix, and that turns out to be really handy later on. So I think at this point I should probably thank you very much for the loan. I should do one other example. Now, in general, finding eigenvalues and eigenvectors is a very challenging task computationally. If your matrix does not fall into some special category, you're probably not going to be able to do it exactly. However, by using computational tools like MATLAB or Octave or something, in all the cases that usually matter for engineering, you can get them numerically. Okay, so let this be our matrix A in this case, and I would like to find all the eigenvalue, eigenvector pairs. You should notice that there's something kind of nice about this matrix. It transposes itself, which is to say that it's symmetric. If you have a symmetric matrix, the eigenvalues and eigenvectors are going to come out to be nice. So that's why this one has been picked. Also, all these zeros in here makes the characteristic equation. And the characteristic equation is this: a determinant A minus lambda I equals 0. So in this case, what I do, in every case, actually, I just subtract lambda down the diagonal. And I compute the determinant and set it equal to 0. And I hope that I can do this without too much difficulty. Now, I suggest that we do a cofactor expansion, because if you notice, we've got a row here with 2 out of 3 entries are 0, or the same for this column. So let's kind of figure out where we're at. This is the plus position, plus, minus, plus, minus, plus. So if I do a cofactor expansion, it's 0 times the determinant of that submatrix, minus 0 times the determinant of this reduced column and this reduced column in that matrix, and then plus a 5 minus lambda times the determinant of this submatrix up here. And we want this to be 0. Okay, well, let's continue the calculation. 5 minus lambda. Now, down here, I got 3 minus lambda squared. And then subtract 4. Five minus lambda times, now inside of here, 3 minus lambda square and lambda minus 3 square are the same. So lambda squared minus 6 lambda plus 9 minus 4. And now that is 5 minus lambda times, all right, lambda square minus 6 lambda plus 9 minus 4 is plus 5. And that is nicely factorable. I'm going to put a minus out here to make this look more familiar. Minus lambda minus 5. And then this factors. And we set it equal to 0. Lambda minus 5, lambda minus 1. So the eigenvalues are, we get a 5 out of this one. We get a 5 again out of this one. And we get a 1 here. So we really hope, if we want to be able to diagonalize this matrix, or if we want to be able to find the full general solution to y prime equals ay, then we are going to need 3 eigenvectors. And that means we will have to be able to find 2 that go with 5. Now, is that true? I don't know. Can we do it? We'll find out. So you start with the original matrix, 3 is in the upper left-hand corner here. And well, it's just this thing right here. And I'm going to plug in 5 for lambda. So 3 minus 5, minus 2, 0, minus 2, 3 minus 5, 0, and 0, 0. Let's see, 5 minus 5 is 0. So that gives what? 3 minus 5 is negative 2, 0, negative 2, 0, and 0, 0, 0. Well, that is pretty handy. We can see, for instance, if you write the vector multiplication that just picks off the last column, 0, 0, 1, that'd be 0 times the first column plus 0 times the second column plus 1 times the third column. Surely that is the 0 vector, right? So 0, 0, 1 is an eigenvalue or eigenvector. People say corresponding to 5. To lambda equals 5. Now, is there another one? Well, yes. Notice these two columns are the same. So if I took, say, the first column minus the second column and ignored the third column, I would also get the 0 vector. So minus 2, 0, minus 2, 0, 0, 0, 0. If I multiply it by this, 1 minus 1, 0. It'd be the first column minus the second column. That's the 0 vector. So fortunately, I got what I wanted. 1 minus 1, 0. I get a second eigenvector corresponding to this eigenvalue. And that's not weird. It's just saying that the the null space of this matrix has dimension at least 2. And as a matter of fact, it's exactly 2. There isn't another one. So there's 2 eigenvectors that correspond to lambda equals 5. We would like one that corresponds to lambda equals 1. Well, our matrix is 3. I'm going to subtract 1 down the diagonal. Minus 2, 0. Next row is minus 2, 3, 0. And then 0, 0, 5. So we're now computing for lambda equals 1. So that matrix, I don't want to say equals because then I don't want to multiply it on the right. So 3 minus 1 is 2, minus 2, 0, minus 2, 2, 0, 0, 0, 4. Same observation, or very similar. This column is the negative of this column, right? So if you add the first 2 columns, you get the 0 vector. Multiply the third one by 0 because it's inconvenient otherwise. So lambda equals 1 corresponds to this vector here, 1, 1, 0. And lambda equals, what was it? I forgot. Lambda equals 5 corresponds to 0, 0, 1. And I think it was 1 minus 1, 0. Yes. All right, so in the language of differential equations, y prime equals ay has general solution y equals, this is a vector y equals C1 V1 e to the lambda 1 t plus C2 V2 e to the lambda 2 t plus C3 V3 e to the lambda 3, and those are both 5s, t. And there's a general solution to this differential equation. It is also true that if you take this matrix, I'm just going to stack these up, 1, 1, 0, 0, 0, 1, 1, minus 1, 0 for the columns, take its inverse, multiply by the original A, 3, minus 2, 0, minus 2, 3, 0, 0, 0, 5, and put this matrix on the other side without the inverse. You will get a diagonal matrix. And what's down the diagonal is predictable. This 1, 1, 0 corresponds with lambda equals 1, so we get a 1. This 0, 0, 1 corresponds with lambda equals 5, so you get a 5 there. And this 1 minus 1, 0 corresponds also with lambda equals 5, so you get a 5 there. And everywhere else there will be zeros. So we have both diagonalized the matrix and we have solved the differential equation y prime equals ay. Now, there are approximately 3.7 bazillion videos online about doing this. So if you do feel like that was too much too soon, or whatever, you can, I'm sure that if you go like to YouTube, or there's the big tutoring site, I can't think of the name of it. Yeah, Khan Academy. Yeah, Khan Academy. I'm absolutely certain you will find this material there. And you could either type in, well, eigenvalues and eigenvectors would be the thing to type in. For a small matrix, you can do it like this. Now, for a big matrix, does anybody do this? No. Perish the thought. If you have an n by n matrix, in general, your characteristic equation is going to be an nth degree polynomial equation. And guess what? There is a theorem in a little bit more advanced mathematics than we're working at right now that says this: if you have a polynomial equation of degree 5 or more, it can be proven that there is no, nor can there ever be, a systematic, formulaic way of solving that. So you're looking at this fifth order quadratic set equal to 0. Well, good luck. Either it has some special properties you can exploit, or you get lucky, or you get a numerical approximation to the roots. So no, for big matrices, people do not do this, but 2 by 2 matrices are actually quite important in engineering. So this is not a waste of time. People actually do this for things other than a summer job or getting a degree in engineering. All right, that's it for tonight. And I will be posting a assignment for this, but let's see, we get back on Tuesday, right? I probably will not make it due on Tuesday because you all were really hoping to have a vacation this weekend, right? So I'll make it due on Thursday instead. Good night.